So we're here in the observatory on Tenerife in the Canary Islands. It's one of the best observatories in the world, and certainly one of the best in Europe, with a great collection of telescopes that carry out all sorts of scientific work, including observations of the sun and the stars and the planets. And we're using a telescope here to do a series of studies concerning black holes and other very energetic objects in our own galaxy. The particular object of interest to the students for the first half of the night is a newly discovered black hole system, and we've been monitoring it very regularly for as long as we can for the last 4 nights, with one more night to go tonight. And the main purpose of the observations is to see if we can find the orbital period of the black hole binary system, to figure out how long it takes the black hole to orbit around the secondary star in this binary. It turns out that if we can do that, we're well on the way to measuring the mass of the black hole in this system. And this is a number that's very important to us for a variety of reasons. It's a number that we can check against our theories for the formation of black holes in our galaxy to see if it makes sense as far as the physics is concerned of the formation of these systems. And also the mass of the black hole is important too, for example, for measuring its spin, which can also be done using X-ray observations. Well, of course, a black hole on its own would be a relatively boring object to observe because it's black. It doesn't really radiate very much radiation of any type, and so it's extremely difficult to see. But one of the ways that we can see black holes is if we put them near objects or put them in situations where there's a lot of local gas. And in those kind of situations, gas can accrete onto the black hole. And because the gravitational pull of the black hole is so strong, the gas gets accelerated to very high energies and the black hole starts radiating. It turns out that the energy of this radiation is quite high. It's in the X-ray or maybe even gamma ray part of the electromagnetic spectrum. And so really the best way to see black holes is if you had X-ray eyes, X-ray vision. Now we're lucky in astronomy that we have that. We have many orbiting observatories that can actually spot the X-ray emission from black holes. And once they do that, one of the goals of the research that we do is to point optical telescopes at the ground, at these X-ray positions, to see if we can find the optical counterparts to these black holes. And in most situations in our galaxy, we find that these black holes are actually in binary systems, orbiting around companion stars that are very similar to our own sun. In more distant galaxies, the situation is a bit different. Not only do we see these black hole binaries in these galaxies, but usually sitting in the middle of these galaxies are much more massive black holes again, black holes of millions, hundreds of millions of times the mass of the sun. But these are still accreting too, not from companion stars, but from disks of gas orbiting around them. But the physics is very, very similar, and they're usually very energetic emitters of X-ray radiation and higher energy radiation too. So we can see black holes in binaries in our own galaxy and in the centers of more distant galaxies as well. We're quite excited about this new black hole that was discovered only a few months ago with an orbiting X-ray observatory called SWIFT. It's a black hole that remains relatively bright both in the X-rays and in the optical, and the latter is important because it means that we can actually make useful observations of it here from Tenerife using the telescope that we have here. And so one of the most important things we can do is to look at the optical light curve, if you like, to monitor the optical intensity of the black hole as a function of time, and to see if that exhibits any periodic behavior that would enable us to identify the orbital period of the system. And this is one of the main things that our physics students here have been doing over the last few nights, and hopefully will finish at the end of tonight's observings. So the UCC students that we have here are doing a kind of wide variety of different types of tasks while they're here, and it's one of the reasons why I think they find this kind of observing trip so interesting. The first thing is to just figure out how to use a telescope like this, how to open and close the dome, use the CCD, not break anything, and point it correctly at objects of astronomical interest. But that's only the beginning of the story. Once we've got the data, then there's an awful lot of data processing and analysis that the students have to understand so that we can actually get to the point of being able to interrogate the data and look for, in this case, the periodic signal that we're looking for from the black hole. And so the UCC students that come here get a very wide variety of different skills from their observing experience here. Not only just pointing a telescope at something, but a wide variety of other data reduction and data analysis skills. And I think this will help them overall in the future in almost any kind of application involving the acquisition and reduction of any kind of data. In addition to the new black hole system that we've been talking about, that we've been studying feverishly for the last 4 nights, many other interesting objects, it turns out, have actually appeared in the sky over the last couple of months too. As I was saying earlier, compact objects, especially like black holes, emit very high energy radiation. Some of that is in the X-ray, but a lot of that too turns out to be in the gamma ray part of the spectrum. More energetic radiation again that we normally see even in the X-ray. Over the last year or so, NASA has launched a new mission called Fermi, which is particularly sensitive at finding new objects in this very high energy part of the electromagnetic spectrum. And Fermi has recently found a series of very high energy objects that we simply don't know what they are, and so part of what the UCC students have been doing here is trying to identify these undiscovered, these unknown sources of high energy emission in our galaxy. But Fermi has also found gamma ray emission from other objects that are slightly more mundane but nonetheless very interesting. Of particular interest to us has been a newly discovered nova, Nova Mon 2012, which was only discovered about a month ago. It's a white dwarf in a binary system that is again accreting material from its companion star. And what happens occasionally is that the material heats up on the surface of this white dwarf to such an extent that it undergoes thermonuclear fusion. And the hydrogen that's been accumulating on the surface of the white dwarf undergoes, if you like, a very dramatic explosion that can last weeks or months, resulting in this white dwarf becoming extremely luminous in the optical, X-ray, gamma ray, radio, etc. The interesting thing about this particular nova, Nova Mon 2012, is that it's been detected as a source even of gamma ray radiation, which is a very unusual type of radiation to see from this type of system. And so we've been trying to study it in the optical to see how well its optical properties compare with its other high energy properties and with the properties of other systems similar to it, but ones for which we have not any strong evidence for gamma ray emission. Once the explosion is finished, usually it returns to a life of quiescence and mundanity for many, many years, 50 years, 100 years, until the material on its surface builds up again very, very gradually to sufficiently high temperatures and densities that you get another explosion like this, and it becomes visible as a nova in the sky again. For some of these systems, the gradual accumulation of material over very, very long periods can result in the white dwarf becoming heavier and heavier and heavier. And it turns out that a white dwarf that reaches a critical mass called the Chandrasekhar mass is no longer stable and explodes as a supernova, a type of supernova. And so there is a link between the type of systems that we're studying, like Nova Mon 2012, and these very spectacular, extremely bright supernovae that occur, that are essentially white dwarfs that completely explode and destroy themselves. And these supernovae are of great interest to astronomers because it turns out that when they explode, the luminosity of their explosion is more or less a constant for this type of system. And so they behave as what's called a standard candle. So if we can see them any place in the universe, we know what their intrinsic brightness is, their intrinsic luminosity. We can compare that to what we observe, how faint they are, and figure out how far away they are. And they are the most important object, really, that we have in cosmology at the moment to figure out the size of the universe. So the kind of object we're studying here plays a role in our understanding of how even these very spectacular supernovae actually behave as well. It's important, I think, for the students here to get experience not only of observing these objects that emit high energy emission like X-rays and the gamma rays, but also other types of systems that we have in our own galaxy that are interesting in their own right. And many of these systems are nebulae, the results of stars that have either completely exploded or just partially exploded in the past. And they can give us very interesting information about how the gas from these explosions interacts with the surrounding interstellar medium, becomes part of the medium, and that from which then maybe other stars can form eventually as well. Some of these objects are not only of great scientific interest, but they are of great beauty as well when you look at them as well. And so the students get a particular kick about getting some very aesthetically beautiful images of some of these novae. We've observed several of these nebulae, and one of which is the Eagle Nebula, which is particularly famous and is a great example of how material can be studied in the galaxy from which stars eventually form. And the students have found these images particularly interesting.